For 100 years, the Panama Canal did exactly what it was built to do. Ships entered from the Atlantic, rose through a series of locks, crossed a narrow strip of land, and descended into the Pacific. The system worked. It moved cargo, it connected oceans, and it shortened global shipping routes by thousands of miles. For most of the 20th century, it was considered one of the greatest engineering achievements in human history. And it was. But the world did not stay the same size. By the 1990s, a new generation of container ships had started arriving at ports around the world. These vessels were longer, wider, and deeper than anything built before. Shipping companies discovered that the bigger the ship, the lower the cost per container. So they kept building bigger. The industry gave these massive ships a name, Post-Panamax. The name itself told the whole story. These ships were too large to fit through the Panama Canal. They had already outgrown it. The canal's original locks were built between 1904 and 1914. They measured 1,000 feet long and 110 feet wide. When construction finished, those dimensions were enormous. But a century later, the largest container ships in service were pushing 1,200 feet in length and nearly 160 feet in width. They simply could not squeeze through. Every time one of these vessels needed to move between the Atlantic and the Pacific, it had to sail around the southern tip of South America. This detour added weeks to the journey and millions of dollars in fuel costs. Panama was watching this happen in real time. The canal generated billions of dollars in toll revenue each year, and that revenue was shrinking in relative terms. The most valuable cargo in the world was now moving on ships the canal could not handle. The largest, most efficient vessels on the planet were bypassing one of the most famous waterways ever built. The math was simple and brutal. If nothing changed, the Panama Canal would become a route for second-tier ships while global trade moved on without it. A structure that had defined international commerce for a century was at risk of becoming obsolete before its centennial was even complete. Panama made a decision. The canal would not be retired. It would be reinvented. Engineers would design a third lane, a new set of locks large enough to handle the modern fleet. This new construction would be built alongside a living, operating waterway that could not be shut down for a single day during construction. The project that followed would become one of the most complex infrastructure expansions ever attempted. And it started with a question that had no easy answer. How do you expand something that the entire world depends on without ever turning it off? The decision to expand the Panama Canal was announced in 2006. The Panamanian government put the question to a national referendum, and more than 76% of voters said yes. It was a rare moment in modern infrastructure history. A country collectively choosing to bet its economic future on a single engineering project. The approved plan called for a third set of locks, one on the Atlantic side and one on the Pacific side, connected by new approach channels wide enough and deep enough to handle Post-Panamax vessels. The estimated cost was $5.25 billion. The timeline was 7 years. Both numbers would be tested before the project was finished. What made this expansion different from almost any other construction project on Earth was the constraint that defined every single decision. The existing canal could not stop operating. Not for a week, not for a day, not for an hour. Every year, approximately 14,000 ships passed through the waterway, carrying around 300 million tons of cargo, container ships, tankers, bulk carriers, cruise liners. The canal collected roughly $2 billion in annual toll revenue. A shutdown of any meaningful length would have sent shockwaves through global supply chains and devastated Panama's economy. So, engineers were handed an almost paradoxical assignment: build a massive new waterway system directly adjacent to a fully operational one, using heavy machinery, controlled explosions, and millions of cubic yards of excavated material, all without disturbing the ships moving through the original locks a few hundred feet away. The scope of what needed to be built was staggering. 2 new lock complexes, each with 3 chambers, each chamber large enough to hold a vessel 1,400 feet long and 180 feet wide. New approach channels on both the Atlantic and Pacific ends, stretching for miles and requiring the removal of more than 100 million cubic yards of rock and soil. The existing Gatun Lake, which sits at the center of the canal system and supplies the water that fills the locks, needed to be deepened and its water level raised to support the increased traffic. Every element of the expansion had to connect seamlessly with infrastructure that was already a century old and could not be taken offline. The Autoridad del Canal de Panama, the agency that manages the Waterway, organized an international bidding process. A consortium of companies from Spain, Panama, Belgium, and Italy won the contract for the new locks. They arrived at a project site unlike anything their engineers had ever worked on before. The clock was running. The ships were still moving, and the ground beneath their feet held 100 years of engineering history that could not be disturbed. The new locks were the heart of the entire expansion. Everything else, the dredged channels, the raised lake levels, the new approach roads and control systems, existed to serve them. So when construction crews broke ground on the lock complexes, they understood they were building the most critical structures in one of the most watched infrastructure projects on the planet. Each new lock complex was designed with 3 consecutive chambers. A ship would enter the first chamber. The water level would rise or fall, the gates would open, and the vessel would move forward into the next chamber. The process would repeat until the ship reached the other side. This basic logic was identical to the original locks built a century earlier, but almost everything about the engineering was different. The chambers themselves were enormous. Each one measured 1,400 feet long, 180 feet wide, and 60 feet deep. To put that in perspective, the new chambers were large enough to fit 4 Statue of Liberty bases laid end to end. The walls were poured from millions of cubic yards of concrete, reinforced with steel, and designed to withstand the pressure of water on one side and the weight of ships that can carry up to 14,000 container units on the other. Crews worked in shifts around the clock, and at peak construction the Atlantic and Pacific lock sites together employed more than 10,000 workers. The gates presented their own engineering challenge. The original canal used meter gates, pairs of massive steel doors that swing open from the center. The new locks used a different design entirely: rolling gates. Each gate was a single rectangular steel structure, roughly 30 feet wide and up to 57 feet tall, that slides sideways on a track built into the lock floor. There were 16 of these gates across the 2 new complexes. Each one weighed around 3,000 tons. They were manufactured in Italy, transported by ship to Panama, and installed with tolerances measured in fractions of an inch. But the most innovative feature of the new locks was something most people never see: the water-saving basins. Traditional locks release their water into the ocean after each use, which means fresh water from Gatun Lake is consumed with every single ship transit. The new locks were designed with 3 lateral basins alongside each chamber. When a ship finishes a transit and the chamber needs to drain, roughly 60% of the water flows sideways into these basins instead of being discharged. When the next ship enters, that stored water flows back in. The system reduced fresh water consumption per transit by 60%, a critical feature in a region where drought had already threatened canal operations in previous decades. While the lock chambers were rising from the ground on both coasts, a parallel battle was being fought underwater and underground across the entire length of the canal. The new locks were only useful if ships could actually reach them. That meant the approach channels, the stretches of water connecting the locks to the open ocean and to Gatun Lake in the middle, had to be completely rebuilt. These channels had to handle vessels 3 times heavier than anything the original canal was designed for. On the Atlantic side, the existing channel leading from the Caribbean into the lock complex needed to be widened and deepened. On the Pacific side, the challenge was even more significant. Engineers had to cut an entirely new approach channel through solid ground. This new channel connected the Pacific lock complex to the existing navigation lane. It ran for miles and required removing tens of millions of cubic yards of material. The excavation included sections of dense basaltic rock that resisted standard excavation equipment. The primary tool for moving that rock was controlled blasting. Drilling crews bored patterns of holes deep into the rock faces. They packed the holes with explosives and detonated them in carefully sequenced charges designed to break the material without sending shockwaves into the operating canal nearby. After each blast, excavators moved in to load the broken rock onto a fleet of trucks running in continuous cycles. These trucks hauled material to designated disposal and repurposing sites. Some of the excavated rock was crushed and used as aggregate in the concrete poured for the lock walls. Nothing went to waste if it could be avoided. Gatun Lake, the artificial lake at the center of the canal, provides the fresh water that makes the lock system function, and also required significant work. The lake's navigational channel had to be deepened from 45 feet to 50 feet across its entire length to accommodate the deeper draft of Post-Panamax vessels. Dredging vessels worked across the lake for months, pulling sediment and soft material from the bottom. They either pumped the material ashore or deposited it in designated underwater disposal areas. The dredging operation on the Pacific entrance was particularly complex. The seafloor outside the Pacific locks contained a mix of soft sediment and harder rock formations. This required crews to switch between hydraulic dredges, which work well in soft material, and cutter suction dredges equipped with rotating heads strong enough to grind through harder seabed. Coordinating that equipment while keeping the existing shipping lane open required constant communication between marine crews, traffic controllers, and the Canal Authority. At any given moment during peak operations, dredges, barges, tugboats, and active cargo ships were all sharing the same narrow stretch of water. By late 2015, the physical construction was largely complete. The lock chambers stood finished on both coasts. The new channels had been cut, dredged, and cleared. The rolling gates had been installed and tested in dry conditions. The water-saving basins were connected and ready. From the air, the expansion looked complete. But looking complete and being ready to operate are two entirely different things, and the people running the Panama Canal knew better than anyone that the gap between those two states is where projects either prove themselves or fall apart. The testing phase began with water. Engineers opened the valves connecting Gatun Lake to the new Atlantic Lock Complex and allowed the chambers to flood for the first time. This was not a simple procedure. The filling and draining cycles put enormous hydraulic pressure on the chamber walls, the gate tracks, the valve systems, and the water-saving basins. Sensors embedded throughout the structure recorded pressure readings, flow rates, and structural movement at thousands of points simultaneously. Engineers watched the data in real time from a control center, looking for any reading that deviated from the predicted range. The chambers held. The basins filled and drained correctly. The gates rolled open and closed on their tracks without binding. Then came the gate stress tests. Each rolling gate was cycled repeatedly under load, meaning with water pressure pushing against it from one side. Engineers measured the deflection of the steel, checked the seals along the gate edges for leakage, and inspected the track mechanisms after each cycle. A few adjustments were needed. Some seals were replaced. Some track alignments were corrected. This was expected. No structure of this complexity passes its first stress tests without refinement. The first vessel to transit the new locks was not a massive Post-Panamax container ship. It was a smaller test vessel, chosen deliberately so that crews could practice the locking procedures, calibrate the tugboat guidance systems inside the chambers, and identify any operational problems at manageable scale. Canal pilots, the specialized navigators who guide every ship through the waterway, trained extensively in simulators before setting foot on an actual vessel in the new locks. The chambers were wider than anything they had worked in before, and the clearances, while generous by design, still required precise maneuvering. The official inauguration took place on June 26, 2016, almost exactly a century after the original canal opened in 1914. A Chinese-operated container ship named Costco Shipping Panama made the first commercial transit through the new locks. Thousands of people watched from the banks. The ship moved through the chambers slowly and without incident. After nearly a decade of planning, bidding, negotiating, blasting, pouring, dredging, and testing, the expanded Panama Canal was open for business. The Costco shipping Panama cleared the final lock chamber, entered the Pacific, and the cameras followed it until it disappeared into open water. For the engineers, the Canal Authority staff, and the construction workers who had spent nearly a decade on the project, that moment was the finish line. For the rest of the world, it was the starting gun. The impact on global shipping was immediate and measurable. Within the first year of expanded operations, the canal began handling vessels that had never been able to use it before. Liquefied natural gas carriers, which require enormous beam widths and deep drafts, started transiting in significant numbers for the first time. American LNG exports to Asian markets, a trade route that had previously required ships to travel around Africa or through the Suez Canal, suddenly had a direct and competitive path. Container traffic on the new locks grew steadily as shipping lines repositioned their largest vessels onto routes that now included Panama. Toll revenue climbed. The Canal Authority reported record annual earnings within 2 years of the expansion opening. But the numbers, as impressive as they were, only captured part of what the project represented. The Panama Canal expansion was fundamentally a story about the relationship between infrastructure and time. The original canal was built in an era when the largest ship in the world was a fraction of the size of a modern container vessel. The engineers who designed those first locks in the early 1900s built them as large as they could imagine needing. They were not wrong. Their structure served the world faithfully for a century. What they could not account for was how completely the scale of global trade would transform in the decades after they were gone. The expansion answered that gap. It did not replace what the original builders created. It extended it, sitting alongside the century-old locks rather than over them. Today, both systems operate simultaneously. Smaller vessels still use the original locks. The largest ships in the world use the new ones. The canal handles both, moving roughly 40 ships per day through a waterway that connects 2 oceans across 40 miles of Central American land. What the Panama Canal expansion proved, more than anything else, is that great infrastructure does not have to be permanent to be enduring. It has to be honest about its limits and brave enough to change when the world demands it. The original builders gave the world a canal. The engineers of the expansion gave it another century.